Do I have any Star Wars? At least you don't have to be a Star Wars fan, but at least Star Wars literate. Okay. There are a couple different movies of Star Wars where this happens, but there are times where when they're flying, they encounter an asteroid field. Okay, that happens in a couple of the different ones. I'm thinking of episode 2, it for sure happens, and then it happens again in episode 7. Anyway, you're getting into your asteroid field, and the pilot has to maneuver to avoid the asteroid field. Okay, I think about slope fields kind of the same way. Your function has to maneuver through a slope field so as not to violate the slope field, not to crash into any of the things that we're going to create. Picture it kind of like that, all right, of what we're going to make. This has to do with differential equations. I don't know why my view is looking funny. Let me see here. Okay. All right, we've talked about function families. These functions all have the same concavity, right? What kind of concavity do they have? Okay, they all have a horizontal tangent. Their minimums are all happening where the slope is changing from. Minimum would be a slope changing from negative to positive. All right, but what makes these functions distinct?
There's a long. Oh, they're on the crosses the origin, like one's at the middle,
One is okay. What makes them distinct? Use the language we've talked about before.
The vertex of
Okay.
The concavity is on the origin.
One of them is on the origin.
And it keeps.
The rest aren't. Where are the rest?
All the way.
Okay. How do we account for that?
They're shifted.
Okay. How do we account for that in calculus? Okay, I heard it. Thank you very much. They all have a different plus c. Okay, so they all have a different plus c. If it has the plus c is 0, that's the one that goes to the origin. But all the rest of them have a different plus c. We call these function families. Okay. Now, if you were flying your spaceship and you entered this graph, say you entered it right here, okay, you would be trapped within this space, right? And that's all that you could, if you're not allowed, it's like the speed skaters and they can't go in anybody's lane, like that's your lane, okay? We're going to see slope fields, they're going to be dotted instead of solid like this. But the function's going to enter the slope fields. We're going to see all these dotted things, and you got to stay in your lane. You cannot move out of your lane with it while you're in there. That's the idea. Here we go. The idea of a slope field. Okay, so slope field is dotted. It's creating potential paths. And then what you're given is you're going to be given an initial condition. You're going to plop your initial condition right on top within your slope field somewhere. So say my initial condition and it plops me in right here. Now I know that my lane I have to stay in is in that lane. I'm not going to go anywhere outside of that. I've got to live in that. I've got to follow the concavity, follow the path of the slope field without violating that. And so that's going to be following the derivative space, right? F prime of x dx. So it's looking at, we know we start with, let me start over. We start with dy over dx, and we know that's equal to f prime. But if we want to separate that and move all of the y things on one side and the x things on the other, then we're going to take our dx away from the left and we're going to bring it over and we're going to have it over here. So that's the separation that we're talking about. This is the only way for us, without a calculator, to handle equations that are non-separable, okay? What kinds of equations were separable? Have to be products and quotients. And then we labeled all the rest of them as non-separable. So anything with a plus, unless it was factored, like the one that Gretchen did. So there was a plus in yours, right? But it was factored, so it was written like a product. So if it's written like a product or a quotient, it is what we called separable, and you can separate and integrate. If it's not, it's what we call non-separable. So the only way that we have to be able to picture it, we can't solve it with any of our other techniques, but we can create a slope field so we have an idea of what it looks like. All right, and so we are going to draw what's called slope fields. You'll do some by hand, and then I've also preloaded a program onto your calculator, which you'll also generate some with your calculator, but we'll learn to do by hand first. Okay, so here's an example. We are given the differential equation dy dx equals x plus y. You cannot solve that with traditional methods because I can't separate the x from the y. The x is added to the y. I can't multiply, I can't divide, I can't do anything in I can't factor. It's simply x from y, but I can create what's called a slope field. All right, so let's look at you know how many of my little leaves now are like? Okay, thanks. All right, let's start at the origin. All right, the origin has what coordinates? 0, 0. So it has an x coordinate and a y coordinate of 0, 0. What would its dy dx value be if the dy dx is following the differential equation we're given? 0. So that's telling me that if you go through the origin, your slope is 0. So what we're going to do is we're going to draw a little tiny baby slope of 0. Not very big, but just if your slope is 0, it's horizontal. What if you were going through, let me pick this point right here. What would your slope be if you were going through that point? All right, well, what are the coordinates of that point? Okay, so the coordinates of that point are 2, 2, and according to the equation for the slope, what's the slope value going to be right there? 4. Okay, that's a positive slope, and it's pretty steep, up 4 over 1. So we're at that spot right there. We're going to draw a slope of 4 the best you can. Okay, it's a picture. If I was going up 4 over 1, it's not going to be perfect, but it's going to show a little bit of a steepness. Eric, pick me another point on here. That's not a point, that's just a -1, what? I don't care, pick me any point that we haven't done. We've done 0, 0, we've done 2, 2, so pick me another one. -1, -1, all right, so -1, -1, he's picking one down in quadrant 3 down there, all right? So, Eric, what would your slope be at -1, -1? -2, all right, so we're going to draw a slope of -2. So we're just doing your best. It should be negative. Okay, what's the difference between drawing a slope of -1 versus a slope of -2? Like, so if you just do this, what does that look like to me? That looks like to me like a slope of -1 because it's perfectly 45 degrees. That would be a slope of -1. So if you want to make it a slope of -2, I'm going to expect it to be a little bit steeper than that. So I would want to see maybe something, you know, a little bit. So it's clearly not straight on the 45-degree diagonal. All right, this is the process of creating a slope field by hand. All right, it is a little bit laborious. When you are required to do this on a test or quiz or AP exam, you're usually given a smaller, like right now you've got, over 20 different points to do. On an AP exam, test, or quiz, you'll probably only be given like 10 or 12 points to do just to show that you know how to do it, but then the rest of the time you get to create it by hand. But let's just go through and keep creating our slope fields. I usually like to do the ones along the x-axis and the y-axis first. So if I'm going to go along the x-axis, I might move over and I might focus on this one right here. Okay, and so I'm just moving over. All right, well that's 1, 0. So the slope is 1. So I know I can create pretty easily a slope of 1 right there. Okay, I'm going to do my best. Is there anywhere else where there would be a slope of 1? 0, 1 would also have a slope of 1. Are there any other places that are going to have a slope of 1? Okay, I heard 2, -1. That's going to have a slope of 1. So we'll find 2, -1. That's right here in quadrant 4. That's going to have, anywhere else going to have a slope of 1? Negative 1, 2. That's going to have a slope of 1. Huh. Look at all the slopes of 1. Notice a pattern? Okay. Is there going to be any place that has a slope of 0? Or besides 0, 0. Okay. Negative 1, positive 1. Okay. That'll have a slope of 0. Where else? Negative 2, positive 2. Where else? Yeah, all along that one. So you start to go, okay, it's not so bad. I can start figuring that out. Interesting, okay? All right, so go ahead and you're going to be filling in, maybe do some more on the x-axis and the y-axis. Okay. So if I move along my x-axis to the right and go to 0, 2, 0, that's going to have a slope of 2. So if I'm going to compare that, these two have slopes of 1. I want to make my next one have a slope of 2, so I do want to be steeper than those if I can be. All right, now look at those. I want you to look at my graph. I went from 0 and across, I went to 1, and then I went to 2. What's happening as we move to the right? Started out flat, then what? Then it goes to 1, then it goes to 2, and then it's going to go to 3 and 4. What do you call that when things are going like this? Okay, could be. Could there be anything else that does that? What else kind of goes like this? Not a log, but exponential but you know what? So does a tangent. Tangent can go like that. But they all have, when I'm curving this way, they all have what kind of concavity? They have positive concavity because they're getting steeper and steeper and steeper. So already we know that this graph has positive concavity, at least right in that section. Yeah?
Wait, like in that section? But isn't there like negative concavity
on the other side? Right. So in this section, we know it has positive. So I'm going to have another negative 2 right here. And I'm going to have another negative 2 right here. So they're following that path. Okay, then I have a negative 3, so I try to make it a little steeper. So if you get trapped in this particular quadrant, if you get trapped in quadrant 1, you're going to start out horizontal at the origin, but then you are going to curve up with positive concavity. Just imagine if you started here and you started following that path, you're going to be having positive concavity as you curve through that. All right. Then maybe we move over and we start looking at what's going on in the rest of quadrant 2. Parts of quadrant 2 are positive, but then parts of quadrant 2 start to have negative. This is going to be negative 1. So is this one. That's going to be negative 1. So is this one. That's going to be negative 1. All the way down. These are all negative. And then these are negative 2, so a little steeper still. And then this becomes negative 3, which is even steeper. And then the last one is negative 4. So depending on where you enter this slope field, you will have to follow the path that the slope field is creating for you. We always enter like we read a book. We enter left to right. So suppose we entered right in here. Okay, if I enter that spot. If I start to follow the path, I swim along with the current, okay, that's going to head me down this direction as I following the current. I'll be swept along getting steeper and steeper and steeper like that as I'm following the current. Well, what kind of concavity does that have? It has negative concavity. Okay, but if I enter right up here, where that 0 is, and start to move, now I'm going to hit a positive number that's going to curve me, and then that's going to curve me, and then it's going to curve me up this way. That's going to have positive concavity. So it all depends on where you get dropped in. All right, now we're going to look at the one on our calculators and see what we can see with that. Okay, so go ahead and grab your calculator. and they'll tell you where your initial condition is going to be. All right, so we are going to, our calculator cannot separate and integrate this equation. We can't separate and integrate it either. So since we can't separate and integrate it, we do our best by drawing a slope field picture, because at least we can tell what kind of cavity it's going to have. So just go ahead to y equals, and in your y equals, you're going to put this differential equation. You're literally going to put x plus y. Okay, so you know where your x button is, you know where your y button is, and for your, your x and plus, your y button, you're just going to hit your alpha key to activate your y button. Did you find y? What number is it by? Number 1. Okay, so you're literally going to just put in what it says, x plus y. Okay, just in y1, I'm going to put it right there. Okay, then you're going to run your program. So go to program and pick the slope field option that I gave you and run it. And it's going to draw the slope field for you. So let me just come around and like look at, I just want to see how your slope field is up there. Yeah, I'll have to reload them on there. You can see the number 1 right there. It has a little y above it. All right, did you run your slope field? What? No, not y1, alpha 1.
No, you go to.
What? Is it working out? Yeah. What was wrong with yours? Yeah. Are the zeros showing up real clearly?
There's a bit of dye anyways.
Are your horizontal pieces showing up?
Oh, wait, no,
So the y-axis. Okay, your window is messed up, so. Yeah, you want to be on a negative 10 to 10 window if you want to make sure. I think that if you check your window, Aiden, you might notice that you're not at negative. Woo, negative 100 to 100. Yeah, we don't want that. Okay. Working okay for you? Okay. So please try and make yourself on a standard window, negative 10s to 10s, and your horizontal pieces should show up really clearly. It's going to get hard for the calculator to show you really steep pieces. And so they're going to start looking like, because they're so steep, what's it going to start looking like? They're going to look like, are they really vertical? No. You got to be smarter than that. These are not really vertical, even though they might look vertical. It's just so steep, the calculator's a little limited in what it can show you. All right, let's keep going. So then you'll be asked, okay, if we give you an initial condition, blank, blank, all right? So like, for example, if I gave you the initial condition negative 4, 0. If we entered this equation at negative 4, 0, we would be swept up in the negative concavity current of our graph. If you're given something that's something other than that, something that's higher than that, not negative 4, 0, but something higher, you would be caught up in the positive current. So you need to just be fluent in moving your different conditions around. All right. Go ahead on the next slide. I want you to imagine, these are 4 different slope fields. I want you to imagine that you got dropped in on your slope field on the dot that was given. Okay, use red or something, and go ahead and try and draw the shape that would be if you were entering the slope field at the point that was given. Okay, go ahead and try that. And try not to hit any of the slope field lines as you're doing it. Okay, try and navigate through those if you can. So I drew one up there. Okay, trying to avoid the slope field lines, but still navigating through those.
Why avoid? This one.
Okay.
Why avoid it?
You're just going to get the most true shape if you do that. I'm going to try that for those 4. Okay, can you go, my Apple Pencil's up there, can you go ahead and draw your answer to E? Denise, can you go draw your answer to C? We haven't done C yet, you want to do D then? Okay, you can go up and use my Apple Pencil on the screen and draw yours. Nathan, you got D? Okay, keep going, all right, so you can go up there and figure D out. Uh-oh. All right. Get this one a little darker. Follow Nathan's. Okay. All right. Hopefully yours match kind of what your classmates thought. Hey, looking at letter A, would there be any places where you could put your initial condition that would change the concavity of your graph? Yeah, if I dropped you anywhere below the x-axis, your concavity is going to be upside down, negative concavity. All right, and the rest of them, no matter where you get dropped, the concavity is going to have the same shape to it. Okay. All right, any questions so far that you're wondering? Okay, here's a couple notes. If the function has a vertical asymptote, like tangent, say, we know that tangent has a whole bunch of vertical asymptotes to it. The solution field that you're given is only, you don't draw multiple pieces, you just draw the section that's on the side of the asymptote that you're given. So you don't have to worry about, like for example, if it was tangent, you wouldn't have to worry about drawing this tangent and this tangent and this period and that period. You just draw the one that is in between the asymptotes you're given. So that's one thing to note about slope fields. The second is if you do have a plus minus. So let's think about that letter A. You would never draw for me both of these things at the same time. Okay? Because that violates the VLT. So it's either the top half or the bottom half, but not both. Okay, so you would never do 2 of those at the same time. Those are 2 things to keep. Okay, so it has to pass. That was where I was wanting you to put VLT. All right, it's got to pass the VLT. Okay, so let's take a look at this one. I want you to practice creating your slope field here. This is one that we could do separate and integrate on, but we're going to practice doing a slope field. So I could do separate and integrate, but we're going to practice drawing a slope field for this one. So I usually work on the easy ones first. I usually do 0, 0 first. And then I usually work on maybe my x-axis ones and my y-axis ones. And then I kind of focus on the different quadrants. So go ahead and create your own little slope field. And I'm going to blank the screen, and then we'll compare our answers in just a minute. touched my forehead, didn't I? It's all over my hand. You forget. You can check. I put some stuff to kind of get you going. See if that looks kind of like what you're doing. I labeled them. 8, yeah, 2 times 2 times 2. Sometimes I find it helps to label so that, like, if I'm grading it, if it's hard to tell the difference between an 8 and a 4, that you maybe put a little number next to it so that you know there's supposed to be a difference between 8 and 4, but it's hard to draw a difference between 8 and 4. The zeros are easy. The ones and negative ones are easy. Those should be obvious. The other ones are harder to do. That's been there for a while. I don't know whose it is.
What up?
Not yours.
I have to leave that break in the back, but I know it's fine. Okay.
Let's see if it even has programs on it. It doesn't have our programs, so it's probably not somebody from this class.
Or like you just want.
Mm-hmm. Although I don't know if somebody which one would actually have that, but. Yeah.
So on the test, I'm label them, because like all my numbers are right, but I'm just like, my 8s and 4s look really similar. If you label them correctly,
Yeah.
would this be an F or a Q or multiple choice?
Usually. Or, I mean, they could do like the slide we had before that had 4 of them. It could be like, which of the following is the slope field that matters? And then you pick it, right? What do you notice about symmetry on this? Are you picking up on that?
It's symmetric.
Yeah, in what way?
Across the
Diagonal. Polar axis.
Okay, so across the y-axis, okay, you would have symmetry on either side, like maybe a parabola, right? So if we were to start here at the origin and we were to go through this, we would be curving up this way. And then on the other side, you would have what's the name of that symmetry? Because that's something that would be good to put in an FRQ. Not odd. It has even symmetry because you have equal sides on either side of the y-axis. That would be called even symmetry. Odd, it'd be like tangent is an odd graph.
like an exponential. Right? Is it?
Exponential does not have symmetry.
I meant like
Like a tangent graph coming up. So first and third, yeah. All right, go ahead and check that one on your calculator, okay? Check it on your calculator just to see if, do a standard screen. In fact, you could even make a screen that was only like -3 by +3, since that's about what our picture is. You could do -3 to +3 instead of -10 to +10. And then double check. Okay, once you've checked that, go ahead and go into your Canvas and find a sample FRQ that deals with slope fields. And then that's what we're going to work on for the next